Okay, good day. In this video, we'll be talking about energy in simple harmonic motion. Energy in simple harmonic motion. Now, we already understand the basic concept of a simple harmonic motion system. It's a system that goes to and fro, and the acceleration is always directed towards a fixed point and is proportional to the displacement. The acceleration is always opposite to the displacement, right? Good. So we already know that basic definition of a simple harmonic motion system. Now, when we talk about energy in simple harmonic motion, we all know that this is a mechanical system we're talking about. So we're dealing with the mechanical energy. And there are two types of mechanical energy, which are what? Kinetic energy and potential energy. Now, let's start with the potential energy aspect. Potential energy, I've already explained this to you guys in class. Potential energy is the what? Is the energy that a system stores based on its configuration or based on its orientation as the current state of the system. Current state of the system. The energy that it has based on how it is at that moment is known as what? Potential energy. So now we are going to take just two different aspects of two different positions of your simple harmonic motion system. Now I'm going to be using a simple pendulum because that's the most common example of a system undergoing simple harmonic motion. Now you have your extreme positions. There are two extreme positions, of course. Each of them are equivalent to each other. And then you have your mean position in the center. Now imagine this: if you place your simple pendulum, just make it sure it's arranged, put it well at the center. Will it move? No, it won't move on its own accord. It won't move on its own accord. Meaning that at that point, it does not have energy to do work because work entails movement. Work is force times distance. So it has to be a distance moved before work can be done. But since there's no movement, there's no work done. And since there's no work done, there was no ability to do work. And since there's no ability to do work, there was no energy based on that position that it was. So that energy that it's supposed to have based on its position is what? Potential energy. And at that point, it does not have it. So at that mean position, potential energy is zero. Potential energy is zero at that mean position. If you go away from the mean position, if you place the bulb in another point, any other point, not at the mean position, you will agree with me that the bulb will fall back down to the mean position. So at any other point, it has ability to do work. So at any other point, there is potential energy. At any other point, there is what? Potential energy. Now, as you go further from the mean position, the potential energy increases until you reach your maximum displacement, which we also call the amplitude. So the potential energy continues to increase until you reach the maximum displacement. At that maximum displacement, that's where you have your maximum potential energy. That's where you have your maximum potential energy. So PE is maximum at your extreme positions. So what we'll do now is we need a formula to calculate maximum potential energy, and we need a formula to calculate potential energy at any time, not necessarily the maximum point. Do you understand? So we need these two formulas now. Now, what is potential energy again? We said it's the energy that the system has based on its configuration. Okay, now I've taught you guys two types of work. I've told you guys that there's work done on system and there's work done by system. Now when a system does work, like the system that uses its own natural operations to do the work, that's work done by system. But when it's an external agent that does the work, that is work done on system. Okay, now work done by system, I told you it uses the system's energy, or let me say it uses the system's potential energy. And since the system's potential energy is being used up, the potential energy drops. So work done by system reduces potential energy, but work done on system increases potential energy. Work done on system increases potential energy. Now we have seen that at the extreme position, potential energy is maximum. At the mean position, potential energy is minimum. So in what direction would we move that when we say that the potential energy was being increased? In what direction do we move to say that the potential energy was being increased? That direction is from mean position to extreme position, not from extreme position to mean position. Because if we move from extreme position to mean position, potential energy what reduces. That means that is work done by system. But when you move from mean position to extreme position, the potential energy what increases, and that's work done on system. So we want to find the work that will be done on this system to bring it from the mean position where potential energy is zero to the maximum position, to the extreme position where potential energy is maximum. So that amount of work that will be done, that amount of work that will be done is equal to the potential energy that the system has at that point. Do you understand? It's equal to the potential energy that the system has at that point. Okay, so we want to calculate that work. Now we know that work is force times distance. Work is force times distance. Now our force is where we have issue with now. Our force is where we have what? Issue with. So this force is not a constant force. We all know that force is mass times acceleration, right? And in simple harmonic motion, acceleration is not constant. It varies with displacement. Does it not? It varies with displacement. Since acceleration is not constant, then force cannot be constant. Do you understand? The force cannot be what? Constant. So in a situation like this whereby you have a varying force and you need that force to calculate your work done, what you simply do is to find an average force. Yes, the force is continuously changing, but out of the various values of the force, you use an average. Now, how do you get this average? You take the final value of the force, add it with the initial value of the force, and then add them up. Okay, add them up, yes, then divide by 2. That's what I mean. Okay, you take the final value of the force with the initial value of the force, and then you divide by 2. You add them and divide by 2. Do you understand? When you do this, you've gotten an average, and that's the average force you're going to use to calculate your work done. Do you understand me? Now, what's the average force? Let's start. What's the initial force? We are going from the mean position to the what? The maximum point, right? To the extreme position. So at the mean position, what is the force on the system? Remember that force is mass times acceleration, and acceleration depends on displacement, does it not? We have our formula for acceleration. So I'm going to be skipping the negative sign. That we all know that acceleration has a negative sign. I'm only going to be working on magnitudes, not directions this time around, okay? Because energy that we're working on is a scalar quantity. It does not deal with direction. So we can ignore the signs at the time being for energy. Okay, so I'm going to ignore the sign of acceleration, omega square y. That's not a formula for acceleration, omega square y. And at the mean position, y is 0. There's no displacement at that point. Y is 0. So acceleration there is 0. And since acceleration there is 0, your force, which is mass times acceleration, becomes 0 as well. Because mass m times 0 is 0. So your force at the mean position is 0. Now, what's the force at the extreme position? So first of all, you have to go and calculate the acceleration at the extreme position. That acceleration A is omega square r. Omega square r. Okay, because we're at the extreme position, that's why I'm using r, not y. Okay, that's your acceleration there. And then what is the force there? What's the force there? F is equal to ma, right? So it's definitely going to be m omega square r. That's going to be your force there. Do you understand? That's going to be your force there. So that is the final force, and 0 was the initial force. So like I said, we add them up. When you add them up, 0 plus mr square, mr omega square is still the same thing as mr omega square, right? Good. So then we divide by 2. So our average force will be equal to m omega square r over 2. M omega square r over 2. Or you can say half, better way to put it is half m omega square r. That is your average force. But then we're talking about the work done. So work done is equal to our average force times the distance, which we said is our average force is half m omega square r, and our distance at this extreme position, the distance at this extreme position is r. So it becomes half m omega square r square. So that's the work done in taking the bulb from the mean position to the extreme position. Do you understand? So that work done is adding to the what? Potential energy. So that will be your maximum value of potential energy. So anywhere, anytime, any day, your maximum potential energy. Your maximum potential energy is half m omega square r square. Omega m square. Half m omega square r square. That's your maximum potential energy. But that's just potential energy at the extreme position. What about if it's not at the extreme position, at another point? Not even this mean position, at another point. So it's still the same process you will take. The only difference now is that at another point, your displacement is not r, it is y, not r. So in that case, your potential energy at any point at all is half m omega square y square, not r square, because you're not talking about the maximum position. Do you understand? So that's the formula to calculate potential energy in simple harmonic motion. And the other one is formula to calculate maximum potential energy in simple harmonic motion. Let's move on to the kinetic energy aspect. Now we say that the kinetic energy is the energy that an object has at its center based on its motion. Based on its motion. And we said that formula for kinetic energy is always half mv squared. Half mv squared. That's the formula for kinetic energy. So we all know that the kinetic energy now depends on the velocity. And in simple harmonic motion, velocity is changing. In simple harmonic motion, what is changing? Velocity is changing. So the truth is this: when you have minimum velocity, you will have minimum kinetic energy. And when you have maximum velocity, you will also have maximum kinetic energy. So now the issue is, where do we have minimum velocity? Where do we have maximum velocity? So we can figure that out from our velocity formulas. Okay, our velocity formula says plus or minus omega square root of r square minus y square. Now the issue with this our formula is on the root part. On this square root part, that's how we take and know minimum or maximum velocities. Okay, so since we're dealing with, let's start with the minimum. Okay, so the minimum now is going to be let's see, the minimum is going to be when the minimum is going to be 0. Okay, that's the lowest value of velocity can have, 0. Okay, so when do we have this 0? When do we have 0? Is when that square root side is 0. When their square roots become 0, everything will become 0, and then your velocity is minimum of 0. Do you understand? Your velocity is minimum of 0. Remember I said since we're dealing with energy, I'm going to be ignoring signs. So let me remove this plus or minus so that we don't get confused in the way. Okay, let's take away that plus or minus. Let's just say V is equal to omega square root of r square minus y square. So we're ignoring signs because we're talking about energy, which is what? A scalar quantity. So the smallest value here has to be 0. And how do we get 0? Is when that my square root side becomes 0. So that I'm saying that r square minus y square must be equal to 0, right? That's what I'm saying. So I'll take the square of both sides. Square, we cancel square roots out. I have r square minus y square equal to 0 square is still 0. Now, I need a particular value of y because it's y that is changing. Our r is constant. The maximum displacement is always constant. Is the y, the displacement at a particular time that is changing, okay? So, I need my y. So I have minus y square. I'm taking the r square over to the other side equal to minus r square. Of course, the negative should cancel themselves out. So y square is equal to r square. And your squares also will cancel themselves out. So y is just equal to r. So when your y, when your displacement is the same thing as your r, whenever your displacement is the same thing as your r, then you have minimum velocity. So when your displacement r is at the maximum position that your displacement is r, sorry, at the extreme position rather, at the extreme position, that's when your displacement is what? Is r. So at the extreme position, we have minimum velocity. And that minimum velocity is what? Is 0. So that means at the extreme position, we also have minimum kinetic energy. And that minimum kinetic energy will also be what? Is 0. Because kinetic energy is what? Half mv squared. And since V is 0, the whole thing becomes 0. So the minimum kinetic energy is what? Is 0 at the extreme position, minimum equal to 0. Do you understand? Okay. Now, where do we now have maximum velocity? Where do we have maximum velocity? Now, this is the thing. I've taught you guys maximum velocity before. I've given you a formula for maximum velocity. It's simply omega r. It's simply omega r. I've already told you guys that is omega r. I've derived the formula for you guys already. That is omega r. Just in case you forgot, V is equal to omega r cos theta, right? And I said that your maximum value of your cosine is always 1. And the only time you can have a cos that will give you 1 is when you have cos 0 degrees. So whatever that cos something becomes 1. So since that's the maximum that we can have, you have V equal to omega r times 1. V equal to what? Omega r. So that's your maximum velocity. I've explained this to you guys already. So at what point is this maximum velocity showing? At what point? Now let's relate it to our formula for velocity. That one has square root. Omega is the square root of r square minus y square. When is this formula going to give us omega r? When is it going to give us omega r? Okay, so you can see omega on both sides. You can cancel the omegas out. Now you can take the square of both sides to remove square roots. Okay, so you have r square minus y square equals to r square. We need y square minus y square equals to r square minus r square, which will give you 0. So minus y square equals to 0. Divide both sides by that minus. 0 divided by minus is still 0. So y square equals to 0. Take the square root of both sides. Your y is equal to 0. So when your displacement is 0, that's when you have maximum velocity. When your displacement is 0. And where is your displacement 0? Your displacement is 0 at the mean position. When it has not moved anywhere, the displacement is 0 at that mean position. So since we have a maximum velocity at that mean position, we will have a maximum kinetic energy. And again, what is that maximum velocity? Is omega r, like I've already explained. So our maximum kinetic energy is equal to half m v max square. We're talking about the maximum kinetic energy, so we should use the maximum velocity. And what's the maximum velocity? Omega r, I mean. So Ke max is equal to half m, okay, and our v is what? Omega r square, which when you expand it, it gives you half m. Not really expand, just open the brackets well. Omega square r square. You take the square and give to both things inside the brackets. Do you understand? So that's your formula for maximum kinetic energy. Now, one thing you will notice is that this is our formula for maximum kinetic energy is the exact same formula for maximum potential energy. Do you understand? Do you see it? It's the exact same formula. It's the exact same formula, okay? So we don't need to cram two different formulas. Formula for maximum PE is the same as formula for what? Maximum KE. Good. Now let's talk about our law of conservation of mechanical energy. Okay, I know I've not talked about kinetic energy at any position yet. I've talked about the minimum kinetic energy. I've talked about the maximum kinetic energy. The minimum occurs at the extreme position. The maximum occurs at the mean position. What about other positions? We'll get there soon. We'll get there, okay? But now, before I get there, let me talk about conservation of mechanical energy, which I've already explained to you guys in class. Conservation of mechanical energy. Now, we all know that energy can never be created or destroyed. I'm talking about mechanical energy now, okay? But can be converted from one form to the other in an isolated system. So, and what we are saying now is that in an isolated system, the sum of potential and kinetic energy remains the same. It's constant. At any point in time, it is constant. It's the same at any point in time. So, for example, let's take the the mean position at, for example, let's take that mean position at a point in time, the mean position. Now, what's the potential energy at the mean position? Is maximum, Pmax. At the mean position, our potential energy is Pmax. And what's the kinetic energy at that position? Is Ke mean, minimum. We all know that potential energy is maximum there. Okay, at the mean position, sorry, potential energy is minimum, rather, is minimum. And kinetic energy is what? Is maximum. Okay, is maximum. Potential energy is minimum at the mean position. Kinetic energy is maximum at the mean position. And what's minimum potential energy? We said is 0. What's maximum potential energy? We said is half m omega square r square. So when you add them up, is half m omega square r square. So this is the total mechanical energy at that position. And from our law of conservation of mechanical energy, this value will remain constant throughout the motion. Whether it leaves the mean position to the extreme or any other point, it will remain constant. Okay, it's going to remain constant. So half m omega square r square is still your formula for total mechanical energy. That's your formula for total mechanical energy. So your total mechanical energy has the same formula as your maximum kinetic energy. Also has the same formula as your what? Your maximum potential energy. So if you see questions asking you find maximum potential energy, find maximum kinetic energy, find total energy of the system, they are all saying the same thing. They are all saying what? The same thing. Do you understand? So that's just one of the things we are going to draw from this our conservation of mechanical energy. We have gotten a formula for total mechanical energy. Now I want to get a formula for kinetic energy at any time, not just at the mean position or the extreme position, at any other time. I have gotten formula for potential energy at the maximum position, that's the extreme position. We said is what? We said is half m omega square r square. At the mean position, we said it is 0. We have also got a formula for potential energy at any time. We said it is half m omega square y square. Okay, we have gotten those formulas. Now, let's go to the kinetic energy. We have gotten a formula for kinetic energy at the mean position where it is maximum. We said it's half m omega square r square. At the extreme position where it is minimum, we said it's 0. Now let's talk about what is in between. Let's talk about what is in between. Now, another thing we will draw from the conservation of mechanical energy is that a change in potential energy is not a disappearance of potential energy. It's actually a conversion into kinetic energy. Energy is not created or destroyed, but it's transformed. So whenever we say potential energy has reduced, it means that it was converted to kinetic energy. Okay, so let's take a particular position that the displacement is y. Let's take a particular position that the displacement is y. Okay, what's the potential energy at that position? We know that it is half m omega square y square, but we don't know the kinetic energy at that position. We don't know the kinetic energy at that position. But I've just told you that total potential energy total mechanical energy at any time remains the same. It remains the same at what? At any time. It remains the same at what? At any time. So what we're simply going to do now is we know that PE plus KE. You see, I don't write PE max or KE max or anything like that. I just write PE plus KE. That's potential energy and kinetic energy at any time is equal to total energy, which we all know the formula for total energy. What is the formula for total energy? That's half m omega square r square. And the PE at any time, we just know that it's half m omega square y square. But the KE is what we don't know. So we just have to make the KE subject of formula. We find out that KE is equal to half m omega square r square minus half m omega square y square. Now you can see that your half, your m, your omega square, they are common for both the first term and your second term. In that case, we will do what is called factorization. You bring out half m and omega square out of a bracket, half m omega square. When you bring them out from your first term, what will be left is r square. Put your minus sign. From your next term, what will be left is y square. Close your bracket. So that's your formula for kinetic energy at any time, at any given time. That's your formula for what? Kinetic energy. Is that clear? Okay, so I actually went through a very long process to tell you this formula for kinetic energy. The reason I went through this long process is for you to see the importance of the law of conservation of mechanical energy. Okay, now I could have gone through a short process, very short process to show you a formula for kinetic energy at any time. You all know formula for kinetic energy, that is half mv squared. And what is v at any time? We know that is um, omega square root of r square minus y square, right? Okay, so we need v squares. For our formula for kinetic energy, we say it's half mv square. So what is actually that v square? You have to just take the square of that your formula. When you take the square of that your formula, omega will carry a square, and then your square root will disappear, leaving you just r square minus y square. So this is your formula for v square. Now substitute it into your formula for kinetic energy. Ke is equal to what? Half m omega square into bracket r square minus y square, and that's the formula that we got. Do you understand? So let's summarize the formulas that we just have now. So let's start with potential energy. Potential energy maximum is what? Half m omega square r square. And where do we have this? We have it at extreme position. Okay, now moving to your potential energy at any time, we said is what? Half m omega square y square. Okay, and then your minimum potential energy, we said is what? Is 0. And where do you have this? You have it at your mean position. Okay, now your kinetic energy at the maximum kinetic energy is what? Is still half m omega square r square. And where do you have it? At your mean position. Okay, and the kinetic energy at any time, we just said that is what? Half m omega square into brackets r square minus y square. And where do we have it? Any position. Your ke minimum potential energy, you have it at 0. And where do you have that? At your extreme position. And then what is the formula for total mechanical energy? The total energy is what? Is the same as your maximum potential energy. Is the same as your maximum kinetic energy, which is half m omega square r square. So those are your formulas for what? For energies, different types of energies concerning simple harmonic motion. I hope it's all clear. The formulas are very simple to use. Very simple formula to use. The only time they can complicate the questions is if they don't give you your omega. Okay, so if they don't give you your omega, they'll give you another information that you can use to find omega. For example, they can give you the length of your simple pendulum. Okay, they can give you the length of your simple pendulum, and you know that you can get the length using the simple formula omega equal to square root of L over G. Omega equal to square root of L over G. They might not give you the length, they might give you the period T. You can use the simple formula omega equal to 2 pi over T. They give you frequency, use the simple formula omega equal to 2 pi F. So when you use this formula, you will get your omega, then substitute it into your values for your energy, and you've gotten your energy that you need. Do you understand? So that is all for energy in simple harmonic motion.